you should be seeing a picture of Neptune. And here we go. I'm not sure how stable my internet connection is right now, but I'll try my best. And if I suddenly dissolve into a whole bunch of gobbledygook, please let me know, either because the internet has decided to hate me or because I'm spouting what appears to be gobbledygook. Because if you have questions, probably other people have questions. So please do feel free to wander up to the microphone and ask me to go back and repeat something. So let's get going. Let's start with some history. In 1781, Uranus was discovered. Up until this point, only 6 planets in the solar system were known: Mercury, Venus, Earth, though it wasn't always clear that Earth was a planet, Mars, Jupiter, and Saturn, 6 planets. It wasn't until 1781 that careful survey of the stars led astronomers to realize that Uranus was moving against the stars like the other planets do, just much dimmer. Uranus was actually often called Herschel in the early days after the guy who discovered it. In 1846, we get to the discovery of Neptune. And the discovery of Neptune happened because scientists had watched the orbit of Uranus, and as time progressed, it was clear that the orbit of Uranus wasn't doing exactly what astronomers would have expected, knowing what we knew about how gravity works and about how orbits work. And so a couple of astronomers independently predicted where an additional planet should be to cause Uranus's orbit to be weird, to be different than what we would have otherwise expected. Lo and behold, astronomers went looking near these predictions, and Neptune was discovered almost exactly in between the two predictions, the two independent predictions made by astronomers. However, it still appeared that the orbit of Uranus didn't quite look like what we thought should be happening. And so people thought, hey, we used Uranus's orbit being funny to discover Neptune. We should be able to do that again. And astronomers made predictions as to where this next planet should be. And then they looked there, and there was nothing there. They redid their calculations and came up with a new prediction, and looked there and nothing. And so eventually there were so many predictions of where this next planet should be on the sky that you could have looked essentially anywhere, at least anywhere within the plane of the solar system, anywhere mostly fitting with how the other planet orbits are oriented. You could have looked anywhere around there and been close to one of these predictions. Eventually, in 1930, Clyde Tombaugh in Flagstaff discovered Pluto through a blind search, which means he wasn't looking towards any of the predictions in particular. He was just doing a survey of the sky and trying to see what he could find. And when I say he discovered Pluto, what do I really mean here? Because this will be important to the rest of the talk. When I talk about observing either planets or Kuiper belt objects like Pluto, what I'm talking about is that you see a point of light and it moves relative to the stars over time. So this, for example, is the discovery of Varuna from 2000. That's multiple images of the same small patch of sky taken at approximately hour intervals. And the Kuiper belt objects, if they're around 50 AU, where 1 AU is the Earth to Sun distance. So if they're 50 times farther from the sun than Earth is, they'll move at about 3 arc seconds per hour. Now, if you don't think about angles on the sky as often as I do, which is fine, 1 arc, there's 60 arc minutes in a degree, and there's 60 arc seconds in every arc minute. So there's 3,600 arc seconds in 1 degree, and a Kuiper belt object will move 3 arc seconds in an hour. This is beyond most telescopes that you and I can get our hands on for reasonable piles of cash. This is a you get observing time on a large telescope sort of an endeavor. So now we have Pluto, and Pluto gets called a planet because we think that it's significantly tugging on Uranus and Neptune. Then in 1949, both Kuiper and Edgeworth separately posit the existence of a belt of small bodies orbiting beyond Neptune. And it wasn't at this time recognized that Pluto may or may not be in this population. The main difference between these two scientists is that Kuiper published in a very well circulated American journal, scientific journal, whereas Edgeworth published in a very poorly circulated Russian journal. And so Kuiper became the one that everybody pointed to as having thought of this idea, but Edgeworth actually came up with it at about the same time. So sometimes if you are naming this region of space after now dead white guys, often you'll hear it called the Kuiper belt. Sometimes you'll hear it called the Kuiper-Edgeworth belt or the Edgeworth-Kuiper belt. And sometimes, if you don't want to name it after anybody in particular, then you might call it the trans-Neptunian belt. I'm pretty strongly in the habit of calling it the Kuiper belt, even though I think I'd like to call it the trans-Neptunian belt and not name it after anybody in particular, but you'll probably hear me call it the Kuiper belt throughout the talk. So then time marches on. In 1978, Pluto's moon Charon was discovered, and this is important because this allowed us to measure the mass of the Pluto-Charon system. You can use Kepler's third law in a general form with help from Newton as to why things work the way they do. And you can calculate the mass in a system from the size of an orbit and how long it takes that orbit to complete. And this was the nail in the coffin for actually Pluto's really small and not very massive at all, nowhere near massive enough to be tugging on Uranus and Neptune like we thought it had been. It turns out, actually, we just didn't know the mass of Uranus and Neptune very well. And once the Voyager spacecraft flew by both of these planets and measured their masses very precisely, all of these extra perturbations on the orbits of Uranus and Neptune just disappeared. They're gone. So Pluto is in no way tugging on either of these planets to a significant measurable degree. But it was the only thing out there that was known, so people kept calling it a planet. And then in 1992, the next Kuiper belt object, the next trans-Neptunian belt object, was discovered, then called 1992 QB1, for reasons that are strange and esoteric, even to those of us in the field, and now named Albion. So let's take a look at the solar system as we now understand it, at least a partial view. But first, just to back up into a little bit of jargon, and I've already used some of this a little bit. when I talk about distances in the solar system, I'm going to use the astronomical unit, or the AU, where the sun to Earth distance is 1 AU. And this allows me to tell you these distances without your brain going, wow, that's big, but not otherwise absorbing what that number is. Because if I told you all of these distances in, say, kilometers, your brain doesn't process the numbers well. But if I tell you that Neptune, it currently orbits the sun at approximately 30 AU, your brain can go, okay, I understand how big 1 is compared to how big 30 is. And your brain actually like processes it and understands the relative sizes of the orbits. Whereas if I told you these distances in kilometers, it wouldn't work as well. Another piece of jargon that I'm going to use is something called the eccentricity. And here I don't mean having a fondness for a very flamboyant style of dress, or a tendency to color one's hair. What I mean is a description of the shape of an orbit. If the eccentricity of an orbit is 0, it is a perfect circle. But as the eccentricity gets bigger and goes closer and closer to 1, the orbit gets squished or elongated, depending on how you like to think about it. And this, it turns out, is a really cool way to get a handle on how poked at, in a sense, an orbit is. If nothing is poking an orbit, the planet forms and then sits on its orbit, it will probably be on an approximately circular orbit. But if there's other things going on and it gets hit by a lot of astronomical sticks, then the eccentricity tends to be higher, which is an important part of the Kuiper belt story later on in this talk. Another piece of jargon that I'm going to use is something called the perihelion. Peri means closest, and helion refers to the sun. So perihelion is when something gets closest to the sun along its orbit. And this semi-major axis, that is the size of an orbit. The way that I will describe how big or small an orbit is I imagine taking the long way across this ellipse and dividing that by 2. I've taken the major axis and divided it in 2, and I call that the semi-major axis. It turns out that this is mathematically the quantity that you want when you go through the math and describe things about how orbits work. This is the most convenient way to talk about sizes of orbits. If your orbit is a circle, then the semi-major axis is the radius of that circle. So post the discovery of Albion, now we know of thousands of Kuiper belt objects. And this is the Kuiper belt. Now this is a plot with a lot of information. So if your brain just went, whoa, don't worry, you're in good company. Along the horizontal axis, that's the semi-major axis. So that describes how big the orbit is. And remember here that Neptune orbits at 30 AU. So that marks the beginning of the Kuiper belt. And then how elongated these orbits are. And really what I want you to get from this plot is that the Kuiper belt is not a simple donut-shaped population of objects, but that there is structure in here. There are places that have more or less Kuiper belt objects. In particular, there are these vertical structures noted here in dark blue, and these are something kind of funny. And actually, it turns out that Pluto is one of these things along the vertical line that's labeled 3 to 2. So what in the what? So let's talk about this. there's a concept here called resonance. And what's happening here is that the amount of time it takes for one thing to orbit is an integer ratio compared to the time it takes something else to orbit. And that means that the two things interact gravitationally in this very particular way. One of the really big examples of this in the solar system is moons of Jupiter. So Io, Europa, and Ganymede. Callisto's not involved in this orbital dance. So for Io, Europa, and Ganymede, Io takes the shortest amount of time to orbit, Europa kind of a medium amount, and Ganymede takes the longest. The length of time it takes for Ganymede to complete one orbit, Europa completes 2 orbits, and Io completes 4. You'll notice that all of these numbers are integers, and they're all small integers. And one of the major consequences of this setup is that, say, Io and Europa, they always pass each other in the same spot. You'll notice in this GIF, assuming that Zoom is properly transmitting this GIF, they turn green when they pass each other, and it always happens at the top, as seen on this diagram. This is something that sets up a situation of repeated kicks. It's like, so the analogy I like to use is pushing somebody on a swing set. If you push somebody at the place where you would naturally just always push somebody on a swing set, you push them, and so their swing builds up higher and higher and higher. And if friction weren't a problem, you could get them going right and good. And that's kind of like what resonance is, that you're pushing something around at the same part of its swing every time. In contrast, if you had two things and they were gravitationally interacting, but you didn't have this setup where they were always pushing each other at the same spot, it would be like pushing somebody on a swing set, but in a random place in their swing. And in that case, you would end up with a very annoyed person, but they wouldn't end up swinging high. All of your pushes would add up to nothing. Whereas if you push them at that particular point in their swing each time, their swing builds up. So resonances are kind of like that. And we'll talk about them in a little bit more detail as we go through. So Neptune and Pluto are doing an orbital resonance dance like this. And it's actually the reason why the orbit of Pluto, shown here in red, can come interior to the orbit of Neptune, and that's fine. How does that work? So an orbital resonance generally is when you have two orbital periods, two different lengths of time it takes for something to go around the sun, and you ratio them, you divide one against the other. If that ratio is a ratio of integers, like 4:2 or 2:1, or in the case of Neptune and Pluto, 3:2, then you end up in an orbital resonance. And we'll talk about this again. The reason that that we end up with the vertical structures that we do in the Kuiper belt that were in dark blue in that plot a few slides ago is that orbital period and size of the orbit, the semi-major axis, are related through Kepler's third law. So if you know the orbital period, then you can calculate the semi-major axis. And I'm not going to talk about the math. I'm just going to assure you that you can do that math, and it's an equation called Kepler's third law. So I want to show you how this orbital dance works. So let's go. The other thing that you need here is that the orbits are phased correctly. They're oriented or timed correctly so that the two bodies don't come close to each other. So I'm going to show you a series of plots that look like this. On the left-hand side here, we're going to have a top-down view of the orbits of Neptune and Pluto. Neptune is in blue and Pluto is in purple. The current location is marked by the dot, and I've got a line connecting the sun to Neptune and the sun to Pluto for visual reference. On the right-hand side, I am going to show you a very special kind of way to look at this, where I imagine that I'm always holding Neptune stationary, so that here the line and the dot for Neptune on the right-hand side are not going to move. And I'm going to show you, relative to where Neptune is, where is Pluto. This is something called the rotating frame, because you're taking your rulers, your ways of measuring where things are, and that is rotating along with the orbit of Neptune as Neptune goes around the sun. So as time progresses, Neptune and Pluto move, but in this rotating frame where I'm holding Neptune stationary, here I'm just isolating out the motion of Pluto relative to the motion of Neptune. So while the left-hand plot is the top-down view of what's really happening, the right-hand plot is an abstract way of looking at how Pluto moves relative to Neptune. And when we do this, some really cool things happen. So here we go. And they go on and on and on and on. And hopefully Zoom is transmitting these things more or less in time with me going. Here we go, more and more. And you'll notice now on the right-hand side, something funny is happening. A little bit more, a little bit more, a little bit more. This is kind of cool, right? So you'll notice that Pluto is going through the part of its orbit very close to the sun, at perihelion, and actually planets and Pluto and everything else that is orbiting around the sun, when they orbit, they don't necessarily go a consistent speed. Neptune goes a fairly consistent speed because its orbit is circular, but for orbits that are eccentric or non-circular or a little bit elongated or squashed, things will go faster when they're close to the sun and slower when they're farther away. And that is what's causing the little whoop-de-doo in the right-hand plot here. And we keep going, keep going, keep going, keep going. Keep going, keep going, keep going, keep going, keep going, on and on and on. Pluto's back to perihelion again. More, 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 more. And they're back exactly where they started. Magic. No, resonance, physics, which is kind of magic, right? Right. As we walked through that progression, Pluto went through exactly 2 orbits, and Neptune went through exactly 3. This is why it's the 3-to-2 resonance. Another way to think about that is that their orbital periods have that 3-to-2 ratio. So this closed shape, this Pluto coming back to the same place in this rotating frame, that is a consequence of the ratio of these orbital periods being very, very close to an integer ratio, where 3 is an integer and 2 is another integer. The orbits are phased, they're oriented, so that the 2 bodies don't come close to each other. The loop-de-loops are a consequence of Pluto's varying speed, which is actually Kepler's second law. So actually here we have actually talked about all of Kepler's laws. The first law being that orbits are ellipses. The second law being that speeds vary in a particular way, which we won't go into detail on. And the third law being that semi-major axis, the size of an orbit, and how long it takes for that orbit to happen, they're related. Huzzah! That was a whole lecture in one of my UBC classes this fall. Anyway, so it turns out that all along this dance, Pluto actually gets closer to Uranus than it does to Neptune over the whole course of its orbit, despite the fact that Neptune's orbit and Pluto's orbit, they cross. Because they're doing this orbital dance and their orbits are oriented correctly, they do not come close to each other at all. Really, because the ratio between the period of Pluto and Neptune isn't exactly 3:2, and because there's other things going on in the solar system that tug on Pluto's orbit a little bit, what actually happens is the shape that you see on the right-hand side wobbles back and forth a little bit. So this is another example of libration. If you're familiar with, say, the libration of the moon's face, this is another place that physicists like to use the word libration. And yeah, this is I think that this is really, really cool. This is a consequence of Pluto and Neptune being in resonance. Now, the 3:2 resonance that Pluto and Neptune are in is not the only one that it is possible for a Kuiper belt object to be in. So here are the rotating frame loop-de wiggly diagrams for a variety of different resonances in these different colors. And one of the things to notice is that things come to perihelion. So Pluto in the 3:2 resonance, for example, gets closest to the sun at very particular places relative to where Neptune is. So Pluto only ever comes closest to the sun when Neptune is about 90 degrees away in one direction or the other. And similarly, not exactly at the 90 points, but other resonances have the same sort of behavior. So if you are looking for a Kuiper belt object and you want to find it near perihelion, do not look near Neptune, because there are no resonant Kuiper belt objects that come to perihelion close to Neptune. The consequence of how this dance works. So if you look at, so this on the right-hand side now is a simulated Kuiper belt, population of Kuiper belt objects based on our current observations. It doesn't look uniform. It's not a uniform donut shape around the sun, that it is very strongly influenced by Neptune. So there is in a sense, Neptune takes a little bit of a bite out of that donut shape, and the donut is a little bit lumpy because of the influence of Neptune. So that was a very large number of slides to explain why these vertical structures exist. These are places where the orbits can get more elongated, they can get more eccentric, and that's still fine because the orbital dance involved will mean that Neptune doesn't chuck something out of the solar system. These orbits can cross the orbit of Neptune, and that's fine if they're at these very particular locations. This is important if we are trying to figure out what the Kuiper belt really looks like, because the people who control very large telescopes will not give us enough telescope time to really actually find everything. We have to make do with a limited sample and try to understand how we're viewing the Kuiper belt. It's like looking at a person, say, but you only have very small windows over them, And then you're trying to reconstruct what they look like overall. So if you only saw half of their face, for example, you might imagine that the other half is symmetric, because humans' faces are usually more or less symmetric, and that gets you reasonably well, but not perfectly. And it's a similar sort of a game when we're looking at Kuiper belt objects, trying to figure out how we view the Kuiper belt influences what we see. When we're talking about these Kuiper belt objects, one of the things that is important then is where we are looking, what direction we are looking. So for example, if we start thinking about Sedna, discovered in 2003 with a perihelion distance of 76 AU, we only found it because we were looking in the right direction at the right time when it was coming to perihelion. And why is that important? That's because brightness depends very strongly on distance. So we have here the sun as the yellow dot, and then sunlight expands out into space and spreads over a sphere. And the size of that sphere increases like the distance to the second power. That's how surface area of spheres goes. It then reflects off of a Kuiper belt object, and then that light gets again spread out over a sphere, and then ultimately gets observed by us on Earth. The end result is that you start with some amount of brightness from the sun, and then it gets spread out, hits the Kuiper belt object, and then gets spread out again. And ultimately, the brightness of a Kuiper belt object will vary like 1 over distance to the 4th power. If that logic escaped you, that's fine. It's a few logic leaps. But the end result here is that if we're looking for Kuiper belt objects, we are much more likely to find them at perihelion than we are when they're farther from the sun. So if things get a lot dimmer when they're farther from the sun, they're they're easier to observe when they're close to the sun, and hard to observe when they're far from the sun, relatively speaking. So if here we have Sedna, we can discover it when it's near perihelion, but we wouldn't have been able to discover it when it was elsewhere on its orbit. So if we've discovered Sedna, thinking again of like, we're looking only at parts of the Kuiper belt object, parts of the Kuiper belt population, the parts that are easier for us to see. If we've discovered Sedna, we know that there should be a further populations of things that are kind of like Sedna, except they don't happen to be near perihelion where we can see them right now. And that ends up being an interesting part of this conversation. As we continue to try to find more and more and more Kuiper belt objects, we start to find ones that have larger and larger and larger orbits, and more distant perihelion distances. And these started to get called extreme Kuiper belt objects because it is reasoned that they're so far out in the solar system that they're not really under the influence of any of the major planets anymore. They're not very strongly influenced by Neptune. And when you get a collection of extreme Kuiper belt objects and all of their orbits are oriented in a particular way, you start to get suspicious, because if they're too far away to really be influenced by something in the known solar system, and they show this pattern where they're all off in one direction and we don't seem to have orbits that are oriented off in the other direction, your brain goes, that's suspicious. That's suspicious, it is. And this is where the quote unquote Planet 9 came from. Because if there isn't anything else out there, then how these orbits are oriented should vary. They should scramble themselves out. This is a plot of how an orbit is oriented versus time for some of these extreme Kuiper belt objects, and how the orbit is oriented should vary. So if we see all of these and they're all off in one direction, either we're observing this population at a very, very special time, which is unlikely, or there's something else going on here. And the question is, what is the something else that's going on? The Planet 9 hypothesis is that there is a planet whose gravitational influence is causing the orientation of these extreme Kuiper belt objects to be the way that it is. And that's not an unreasonable idea if you believe that this collection of extreme Kuiper belt objects is representative of the true population. However, there are some things, there are some caveats that were hidden in that statement. Observing the Kuiper belt is ridiculously hard. Objects at this distance are very dim, and they move very slowly. We certainly don't know of all of these Kuiper belt objects that have these extreme orbits, because we can only see these Kuiper belt objects when they come to perihelion. And so there must be some that we can't see that are off more distant, that are not observable to us at this time. The current bunching and orientation could be chance, but it could also be observational bias. As we have discovered more and more and more of these extreme Kuiper belt objects, this pattern, which has flopped sides, you're not imagining that. It used to be one way, and this diagram flops it the other way for reasons known only to the people who made this plot. Not me. As we've discovered more and more and more extreme Kuiper belt objects, the story here is becoming less clear. There's a less obvious preference for a particular orientation of these extreme Kuiper belt object orbits. And in addition to this, there is, we know, some preferred directions to look based on where telescopes are on Earth's surface and what weather they have, and where the galaxy is. So there's a couple of places where the plane of the galaxy intersects the plane of the solar system, and there's a lot of stars in the galaxy, as I'm sure you've noticed. Whenever you point your telescope at a very random part of the galaxy, there's lots of stars there. And if you're looking for tiny little dim pieces of light that go boink, boink, boink relative to the stars, it's kind of unhelpful if the entirety of your field of view is stars, because then you'll miss the little point of light that is the Kuiper belt object. So we can't observe the Kuiper belt very well at all in these two places where the galaxy and the plane of the solar system intersect. And in addition to that, there's a couple of directions where it's hard to look because, for example, the weather in Hawaii is particularly bad in January and February. And the weather in Arizona is particularly bad in July and August because of the monsoon season. Something I never knew before I moved to Arizona, that Arizona has a monsoon season, and it's in July and August, so you get used to low humidity. And then in the 2 months where it is hottest, it is also the most humid, which is not fair. Anyway, you can if you do a detailed deep dive into observations of Kuiper belt objects, and to a lesser extent the asteroids, you can tell that there's certain months that are worse for observing from various sites. So here we are. And these cones, I forgot I had this plot. These two cones are where the galaxy is, more or less. And yeah. I am actually involved in a survey that's going to try to look in several directions, kind of equally oriented around the sky on the plane of the solar system. It's called Classy, and it's really classy, guys. And hopefully it will give us a better statistical understanding of how real or not real this apparent clumping, this apparent clustering of extreme Kuiper belt object orbits is. Because the current sample of extreme Kuiper belt objects is, it's hard to understand the situation in which all of these were observed or discovered, because a lot of that information has been lost. So you can't do really good statistics and try to figure out whether or not you would or wouldn't have seen something else. So it makes it hard to do statistics on figuring out what the underlying population looks like. So we're going to do observing the distant Kuiper belt really well, and try to tell you all whether or not Planet 9 actually exists, among other science goals. So Planet 9 may be real. There's a lot of things that that make the story a bit more complicated than it typically appears in the press. And in addition, if Planet 9 is real, it might not necessarily look like the original authors really conceived it, because this story is something that we now better understand. It makes it more complicated to try to figure out exactly what Planet 9 may or may not be, and exactly what its influence is. So there's a lot more to come here. And hopefully, even if Planet 9 doesn't exist, we'll have learned more about the Kuiper belt, which is exciting. So I've talked a lot about the Kuiper belt, but is there anything past that? One of the really cool things we have is comets, and there's a rather visible comet right now, which I'm sure you'll hear about later in the sky this month. Because we see comets, we know that there is another population out in the distant solar system. So here's, I believe this is Comet Hale-Bopp, and here is Comet 67P, observed by Rosetta. And because we see comets coming into the inner solar system from all different directions, more or less the same in every direction, we can presume that there is a population, which we call the Oort cloud, out very, very distant from the sun. It's so distant that while these things are gravitationally bound to the sun, the rest of the galaxy is really important. So gravitational influence of other stars and the rest of the galaxy pulls things from the plane of the solar system into this more or less spherical shape. And then as things in the galaxy move around, sometimes one of these things ends up knocked into an orbit where it comes into the inner solar system, and we see it as a comet. So this Oort cloud is really very distant. Remember that the Earth is at 1 AU and Neptune is at 30. And this Oort cloud is at about 300,000 AU, if I remember correctly. It's about a third of the way to the nearest star. It's ridiculously distant. But we know it has to exist because we see new comets all the time. One last thing to touch on before I let you all go is that I can't talk about the solar system beyond Neptune without showing you pretty spacecraft photos of Pluto, because that would just be a crime. But first, I'm going to show you a picture of Neptune's moon Triton, just to subvert your expectations. We believe that Neptune's moon Triton is a captured Kuiper belt object because it's orbiting Neptune backwards from how it should have if it was a moon that formed around Neptune. So we believe that a pair of Kuiper belt objects came in and came close to Neptune. Triton stayed around Neptune, and the other Kuiper belt object flew off with the extra energy and angular momentum so that Triton could stay bound to the Neptune system. So Triton is an interesting example, probably, of a Kuiper belt object, but one that has gone through some stuff from being a moon for most of its life instead of free floating out in the Kuiper belt. So now let's get into the New Horizons pretty pictures from Pluto. It visited Pluto in 2015. This was actually the first time that I was ever on TV. I was in Toronto at the time, and CBC, yes, that's CBC, called the Department of Astronomy and said, "Do you have someone who knows anything about Pluto?" I'm like, "Yes." So I ended up watching a New Horizons press conference with no prior knowledge of what they were going to show in CBC studios, and then commenting on it, apparently intelligently enough that they asked me back. So yay. But that was really fun, actually. That's when I learned that science communication was a thing that I really enjoy. But anyway, let's look at Pluto. Here's Pluto. It's awesome. It's got this heart-shaped thing. It's probably a glacier of nitrogen. And most of its surface is dirty water ice. Here's a close-up where the heart-shaped glacier is on the right-hand side, and some of Pluto's dirty water ice bedrock is on the left. And we see some of these mountains here semi-ingrained in the glacier. Here's another nice picture of that. And if you look closely, you can see patterns in the glacier, again, here on the right, that look like convection cells, like as if, imagine water boiling, or like the granule nature of the surface of the sun from the convection cells. Same physics, just a lot slower because it's cold. We think that the nitrogen ice that makes up this glacier is actually convecting, which is really fun. Also, because it turns out water ice is slightly less dense than nitrogen ice, these mountains that are in the middle of that glacier are partially floating in the glacier. They may be they may also be grounded on the bottom, but they are partially supported by buoyancy, like an ice cube is floats in water, because the ice cube is less dense than the liquid water. Same here, except we're talking about solid ice and solid nitrogen ice, and the nitrogen ice is heavier than the water ice. So yeah, there's your fun fact for today. Nitrogen ice is more dense than water ice. We think that there's a lot of interesting things going on in Pluto. Here's an artist concept of the broad strokes. We do think that Pluto, at least in the past, if not now, has a subsurface liquid ocean, which is has an interesting influence on its geology. And I know enough about this to know that it's really interesting, but not enough to really give a great talk on this standalone. And if you're interested in that topic, I can give you suggestions for some people to bring in as guests. Pluto is not alone in its system. It also has a very large moon called Charon. And here's Charon. It's that that little mop of red on its top is probably dust from Pluto. Pluto's redder than Charon is. The Great Big Canyon across Charon is probably because Charon had a subsurface liquid ocean that then froze. And then when liquid water went to ice, it expanded. You do this all the time when you explode pop cans in your freezer, same physics. So as the liquid subsurface ocean becomes solid and it expands, that means suddenly Charon doesn't have quite enough surface, quite enough skin to cover its inside. So the surface expands. And that's where we think we get this Great Big Canyon right across the middle. Is that's a feature of Charon's skin expanding and cracking and breaking apart. Now, New Horizons also flew by a body now called Erica. And here's the best image. It's actually the best black and white image painted with the best color image, where the best color image is a little lower resolution. This is really cool because there haven't been very many impacts onto this body. It hasn't been hit by a lot of stuff. So a lot of the surface features here are not from it being hit by stuff, which is where the surface features for like asteroids come from. So the surface features here are probably consequences of how planet formation works, actually, because this thing formed and then it hung out in the Kuiper belt and just didn't have anything else happen to it. So this lumpy nature, probably something to do with planet formation. The fact that it's got this dual lobe shape, probably something to do with planet formation. And exactly how that has to do with planet formation is still something that people are working on. But it's going to be really cool over years to really deeply think about how this helps us understand how planets and everything else in the solar system formed. Yeah. It's also pretty flat, which is kind of cool. Kind of like a walnut attached to a pancake is the analogy I've heard. So in summary, observing the Kuiper belt is hard. There may or may not be another planet in the distant Kuiper belt. This is something based on orbits of extreme Kuiper belt objects that appeared to be aligned or grouped together. If this alignment is real, which it may or may not be, maybe that might be something from a planet. We do not know of any direct detections of Oort cloud objects yet, but that makes sense because they're ridiculously far away from us. But we know the Oort cloud has to exist because we get fresh comets. And that is our current understanding of the solar system beyond Neptune. Thank you.
Hey, Christa, when you were showing us the orbital resonance there and it made that little loop, from Neptune, if you were looking at Pluto, would that appear to be it going retrograde?
Yeah. I mean, yeah. Actually, yeah. It would be an interesting thing to look at from Neptune because you'd also get a little bit of a distance change. But yeah, it would go retrograde for a little bit.
Okay, thank you.
I have a couple of questions. One, just I think you said Sedna was something like 79 or 76 astronomical units away, and then there was another diagram in which showed Sedna, and it was like 500.
Yeah.
What was that difference there?
So the perihelion distance, Sedna's closest approach to the sun, is 76 AU. But the overall size of its orbit, its semi-major axis, is 500 AU. So it's a very elongated orbit. It comes close to the sun, at 76 AU from the sun, but its overall orbit size is a lot bigger.
Okay, and the second thing was when you were showing that elaborate chart, with all of the objects, and then there was those vertical like lines. Okay, so I just want to make sure I get this right. Okay,
Yeah.
the vertical lines represent a whole bunch of different objects at that average distance, but because they're in resonance, there's a whole bunch of them. But some of them have large elliptical orbits or very elliptical orbits, and some are very circular. Is that correct?
Yes.
Okay.
So each of the dots on this diagram is a distinct Kuiper belt object. And these the verticalness of the fact that they're all at the same semi-major axis, that is because they are in that particular resonance, and that particular resonance has a particular semi-major axis. And they extend to higher eccentricities. Objects in these resonances can have higher eccentricities without suffering a gravitational close encounter with Neptune.
Okay, and the other thing is, as you look at that chart, same chart, it just occurred to me that as you're getting farther and farther away, you're getting a sort of a trend to being more and more elliptical.
Yeah.
More eccentric. And is that perhaps a bias due to the fact that they have closer perihelions? Or
Yes.
is that?
That's exactly correct. There is, so if you look between about 45 and 50 AU, if we're thinking about the 50 AU, 55 AU distance, the lack of objects at low eccentricities at those distances is real, because we could have observed those if they existed, and it appears they don't. The interpretation of that is that the Kuiper belt originally extended to 47-ish AU, and then past that, planet formation timescales were just too long or something along those lines. And then that this tail of the Kuiper belt to more elliptical orbits at larger orbit sizes is because the Kuiper belt has been whacked by a variety of gravitational sticks, including the influence of Neptune. There is a lot going on this diagram.
Okay. Are there any questions from the audience?
So
Yes, go ahead, Roy.
First, what would be the AU location of Planet 9, if in fact it exists?
Okay. So did you catch that?
I did. It depends on who you talk to. Which is, well, it's one of the reasons, don't tell Mike Brown that I don't think it exists. Because so to do what they think it's doing, it has to be massive enough to do this, and you have to have not seen it yet, and there's a whole bunch of considerations that go into this. Exactly how is the orbit oriented and all of that. So there's a range of possibilities depending on exactly how massive the planet is. I think the favored viewed as most likely semi-major axis for Planet 9 is somewhere in the 400 to 600 AU-ish range. And they think it's probably closer to aphelion, to being farther from the sun, than it is to being closer to the sun, mostly because we haven't seen it yet.
Okay. So if it's invisible, maybe it's just far away, as opposed to it doesn't exist.
Yeah.
Okay.
We'll see. I think we'll keep discovering extreme Kuiper belt objects and try to do it in a observationally statistically rigorous way, so that we can get a better understanding of whether or not Planet 9 does exist.
Okay, any other questions? Yes, go ahead. Yeah.
Bruce, I think I should mention the Corbett hypothesis about Planet 9. One, it's Romulan, and two, it's cloaked.
Okay, so there you
Yeah.
go.
There's so
Put that in.
an earlier version of this talk was basically a what is Planet 9 and what is not Planet 9 talk. So I had to I went through the variety of extra planets that have been proposed in the solar system, and I'm like, well, that this is what Planet 9 is, but it's not Nibiru, and it's not Tyche, and it's not all of these other hypothetical things that funny. There was, for real, a hypothetical planet named Vulcan, interior to Mercury, to explain why Mercury's orbit orientation was changing more quickly than we would expect. Turns out it's actually general relativity. Thanks, Einstein. But for a while, one of the people who predicted where Neptune should be said, well, maybe we can solve the Mercury problem with another planet too. And he proposed this extra planet, which he called Vulcan, to be interior to Mercury. So the planet Vulcan does not appear to actually exist in our solar system, but there was a period of time where we seriously thought it might.
Okay, yes, go ahead, David.
Objects in the Oort cloud captured by the solar system's gravity?
Probably there. So the end stage of planet formation was messy, where there was a lot of small stuff left around at the tail end, and not all of it got incorporated into a planet. Some of it got left over in the asteroid belt, some of it got left over in the Kuiper belt, but some of it had a close encounter with Jupiter and got whapped to a much larger orbit. And then once it got far from the sun, the influence of the galaxy changed its orbit to have it reside out in the Oort cloud. Our Oort cloud population is probably a mix of things that originated in the solar system and got chucked by primarily Jupiter, and a mix of things that got chucked from at the end stages of planet formation from other planetary systems. It depends on how. So stars, when they form, they tend to form in clusters, like the Pleiades, for example. How much of our Oort cloud was originally our own depends on how embedded the sun was in its birth cluster at the time the sun was forming. It depends on a lot of things. How many other stars were around, how many of them were undergoing planet formation at the time. With a variety of stars, you might end up in a situation where all of your cloud gets stripped, or you might steal the Oort cloud of another couple of stars. It really just depends on a lot of happenstance and how embedded you are in the cluster at the time.
So objects in the Oort cloud, are they remnants of second and third generation stars? Disintegration, or?
No, so they're probably a lot like asteroids or Kuiper belt objects, things that underwent the planet formation process in whatever planetary system they started in, where planets form from repeated collide and stick events of solid stuff in the protoplanetary disk. They would have built up to a certain size and then had a gravitational slingshot, a gravitational close encounter with a large planet, and that would modify their orbit and chuck them out of the solar system or whatever star system they started in. So think some asteroids, some Kuiper belt objects. Essentially, like what are comets before they come close to the sun and get the coma and the tail.
So the majority of items in this discussion are of items within our or near proximity to our sun and our solar system. What's the distance to the very next sun or star?
See, in astronomical units, if you could do that, what is the distance to the nearest star?
So I think the reason 300,000 stuck in my head was actually because that's approximately the distance to the nearest star. And the Oort cloud is at about 100,000 AU, approximately a third that distance.
Okay.
So it's 300,000 didn't change. So 320,000 or something like that. It's approximately 1 parsec or 3 light years.
Okay. Okay. So good question there. Yeah.
Yeah, it's a unit conversion exercise.
The actual distance to your cloud is more like 100,000 AUs, 300,000 roughly is the distance to the nearest star. So,
And you're gonna meet the Oort cloud for the next star.
there you go, right? And then in between it's no man's land.